Hi, welcome back. Now there are three special cases we can use when we are writing a Taylor series, and they all involve the Maclaurin. Now remember, for Maclaurin is where c equals 0. Now if c equals 0, we have a special case that we can write them to go much quicker. The first one is e to the x, followed by sine of x, and then cosine of x. And we're going to generate these real quickly. It won't take us very long. So I'm going to generate the series for e to the x, just like we did in part 1 for that one. The difference is we're not centered at 2, we're centered at 0 down here. So if we go ahead and start this one, I need my function. It's just e to the x. Now I'm just going to take a few derivatives because, as you notice, e to the x is kind of boring. It's just e to the x every time. So if I want to find the value of the derivative at 0 here, well, that's just 1. That's just 1. That's just 1. Everything is just 1. So if I want to write this as my series, so remember, I'm going to use my Taylor series x minus c to the n, right? So I can rewrite e to the x as the following. The first one is just 1. Remember, this is 1 basically over 0 factorial x to the 0. If you want to write it that way, remember this is where n is 0 here, plus the next one, n is 1. So 1 over 1 factorial x to the first. Now, I don't have to write down x minus 0 because it's a Maclaurin. Now, let's do 4 terms, right? So there's my next one, plus 1 over, this time n is 2 factorial x squared. Now, I only have 3 terms here, but I want a 4th one. Well, hopefully we kind of recognize, hopefully we kind of recognize that, yeah, there's a pattern. We're going to get 1 over 3 factorial x cubed. Now, this right here is just my Taylor polynomial. Normally, for a polynomial, we would have a squiggly equals because it's an approximation. But if I go out to an infinite number of terms, it becomes the same exactly as e to the x. So to show that, I'm going to add an infinite number of terms. So I go plus dot dot dot. That means it goes on forever. Equals, and then I'm going to write my general term. N equals 0 to infinity. And I just look at the pattern. This looks like x is just... it's just x to the n over, now look at that, n factorial. Now I can clean this up a little bit. This is just 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus dot dot dot, which is equal to my series, n equals 0 to infinity, x to the n over n factorial. And that's how we can write our series right here. Very easy to do. Now, from now on, anytime we see e to the x, we just want to memorize this and we can use it, which we'll see in example part 3. Now, to get the series for sine of x, we do the same thing. I look at the original function, sine of x. The first derivative is cosine of x. The second derivative is negative sine of x. And I'll just go to the third derivative here. I get negative cosine of x. Because again it's Maclaurin, I want to find the values of each of these at 0. Sine is easy, 0. Cosine is 1. Sine is 0. Cosine, negative 1. So if I want to write sine of x, I could write this as 0 plus, be careful, 1 over 1 factorial x to the first plus 0 minus 1 over x, be careful, cubed, 1 over 3 factorial, x to the third. Now I'm going to clean this up a little bit. It does go on forever and ever and ever, but I'm going to clean this up a little bit, make it look a little bit nicer so we can see a pattern. Sine of x will equal, ignore all the zeros, this just becomes x minus x cubed over 3 factorial. So it cleans up much nicer. Now remember, we want to go out 4 terms. So notice the pattern. Well, what do you think the next one is going to be? Oh yeah, plus 1 x to the 5th over 5 factorial. There's 3 terms. The next one, you noticed it, it's alternating, minus x to the 7th over 7 factorial. And there's my 4 terms. Now I have to get the general term. This, you need the plus dot dot dot, say we go out to infinity. And now I write my summation, n from 0 to infinity, and I plug it in. Now this is an alternating series, so I put my negative 1 to the n, Look at the x powers. They're all 1. They're all odds. So I go x to the 2n plus 1 over, look, same power on bottom, 2n plus 1 factorial. Now, here's the kicker. Sometimes people think, Mr. Warnow, but we didn't include the zeros in here. Doesn't this generate zeros? No. This will only generate our terms, and you can easily see that. If I let x be 0, that's 1. That's x to the first, and that's 1 factorial. If I let x be 1, 0, next term is 1, right? This is n equals 0, n equals 1. That's different than over here. This series does not really have anything to do with over here. It's how we generate this series right here. So we're done with this part. We're just trying to like match these up. So here n is 1. If I let n be 1, I get negative 1 x to the third over 3 factorial. So it does build my series here. Now you can do something different. I could let n equal 1 here, but that's going to change my power up here. I would have to make this 2n minus 1 and this n minus 1 in this power. So I like to start with n equals 0. Now, how can we, so there's sine. So anytime we see sine of x, we got this. Now notice, sine of x is odd. Well, that should be true. All these powers are odd. So a way to remember how sine of x is, you're just looking at all the odd powers of x, because we know from algebra 2 and pre-cal, sine's an odd function. So and you can see that in the series itself. So if I want to generate cosine of x, now I could do the same process, but I know sine of x. I can take a derivative. Well, the derivative of sine of x is cosine of x. So therefore, to get cosine of x, I'm just going to take these derivatives. I get 1 minus, be careful, if I drop the 3, I get x squared on top. But let's take a look what happens here. I'm going to get 3x squared over 3 factorial. Well, we know 3 factorial is just 3 times 2 factorial. I can cancel those 3's out. Oops, the 3's, not the x. And that's going to give me x squared over 2 factorial. And you kind of see the pattern. This is going to become plus. If I drop the 5, I'm going to get x to the 4th, and the 5's will cancel, 4 factorial. Minus, I drop the 7, I get x to the 6th, the 7's cancel, I get over 6 factorial plus dot dot dot. And now I do my general term, n equals 0 to infinity. Again, it's alternating, so I go negative 1 to the n. But this time, all my powers are even. So I get x to the 2n over 2n factorial. Very easy to do. That's an x, right? Let me rewrite that part right here. That's x to the 2n. Make it look a little bit prettier for us. And notice again, here where sine's an odd function, cosine is an even function. And all my powers are even. Just kind of a neat way to remember it. Okay, now that's the end of part 2. Now if you go to part 3, we're going to take a look at how we can use these to manipulate some things.